everyone. It's a pleasure being here. Thank you, Gregor and Claudia, for having me here. My name is Jonas Weiss. I'm from IBM Research in Zurich. I live just across the street here. I'll be talking about, I have to put the glasses up, I can't see otherwise, how AI to mitigate climate change impact on specifically Swiss society and economy. Everything I'm going to tell you, it's not going to be much technical models that, as you've just seen, is in the context of a white paper that we've been compiling over the last year. So, will climate change really affect us in Switzerland? What do you think? Yes, of course. Thank you. No question about that. And I think it's probably a realistic assumption that we're going to end up in 2100 with like 2.5 degrees or even more if we continue the way we're doing today on a global scale. That means we're going to have a lot of things changing. We're going to have heat waves, cold is going to be less, 0-degree line is going to go up, glaciers going to go. We're going to have more sunshine, which is going to be nice, but we're going to have less snow, so less skiing in the winter. Now, in order to understand and deal with all that, we have to talk about risk. We have to try to understand, like, what does that mean in terms of risk? How are we going to be affected as a society, as a community, as individuals, as corporations? And to quantify risk, you have to start to kind of quantify what actually is causing the risk, but then you also have to understand how vulnerable are you to the risk and how exposed are you to the risk. And this is like typically shown in this risk propeller, which is very often used in the insurance industry. You might have seen that before. But when you talk about climate change and the risk of climate change, there is more to it. There is not just the risk of the climate effect itself, but there is also this so-called transition risk. That means on our journey towards a higher temperature planet, we're still going to try to mitigate, we still have to adapt. So that means like legislation is going to kind of burden us with some kind of regulations of what we have to do as entrepreneurs, as businesses, as probably even as individuals at some point. It's going to affect us. But it's also from a customer and consumer side, we're going to have like pressure from the economic side. So these transition risks, this vulnerability is then more like expressed in how is our ability to cope with these kind of requirements. And when we talk about exposure, it's more about the applicability. So are we actually affected by these regulations, by these effects from economy and from society? Now, again, if you want to manage, we have to understand. So if we talk about climate, I mean, we heard it just in the presentation before, there's water. It can have too much, it can be not enough. Same with heat and cold, thunderstorms, there's many other things. On the legislation and economic side, there is, for example, the requirement to report your carbon or equivalent carbon emissions, ESG reporting. These are the kind of the effects, the things, the events that kind of lead to the risk in the transition or in the physical world. And if you talk about how sensitive is my business, I mean, I'm with IBM, so we talk about business B2B. It of course affects us all in the end, also as a society. Think of supply chain. If your supply chain is vulnerable, your business is vulnerable. If your supply chain is somewhere else where it is vulnerable to whatever, even tropical hurricanes. That means your business here in Switzerland is going to be vulnerable to towards tropical hurricanes. The same with the location or the exposure. So the proximity to water, if it's too much, not enough, but you might actually require it for your processes. Now, what tools do we have to quantify and to kind of measure these quantities to be able to, in the end, assess what the actual risk for our business, for our enterprise, whatever we do is? So, I haven't been here this morning, I have to apologize, so if I'm telling stuff that you already know, you just shout at me. I mean, you probably heard the AI models which are able to predict climate and weather phenomena that have been published recently. It's amazing what these kind of tools can do. They rely on data being produced mostly by traditional models, but nevertheless, what they can do now, I mean, they have factors of thousands faster in execution, and accuracy or the skills that they have is kind of comparable with what we have today. On the legislation side, we have, for example, advanced AI search tools which help you understand which reports, which laws are going to be relevant for you, to which you need to adhere. On the sensitivity side or on the vulnerability side, it's if you don't really know it, then there is like AI tool that can help you mapping. You can inspect your infrastructure to understand how vulnerable is the stuff that I'm actually dealing with. When you go to where is my stuff, if you don't know, you might use some global mapping tools that we've seen before that help you with like ship detection, for example, or other kind of supply chain relevant or asset relevant detection and segmentation stuff to understand where your stuff is. Now, if you have a quick look at what these AIs can do, it's a lot of things that we want to do is like what we just heard before is predicting. It's predicting the future, right? That's typically what predicting is about at different scales. So we have nowcasting in the weather space, and we have climate predictions on the longer term, and there's something in between. And there's like climate is going to be important for our long-term planning for politicians. Nowcasting is for aerospace industry, for kind of planning flights, and everything in between can happen. Now, in order to make these forecasts, of course, we need some data. This data comes obviously from Earth observation, from satellites, but also from ground-based radar stations, from sensor networks that we have. Models, we have ensemble forecasting, probabilistic model, and other kind of tools. And on the large scale, very often with Earth system models, which help us understand where the planet is actually going and where it is. Now, particularly when we look at climate-related models, we often have a relatively coarse resolution. So, I mean, we're talking kilometers, tens of kilometers, even 100 kilometers of the output of the models. We've heard, like, if you go much lower in the resolution in the dam, you have, like, factors of higher compute costs that you have to deal with. Now, fortunately, if we talk about Switzerland, I have to kind of, as the title says, it's about the Swiss economy. Sorry to be a bit local here. We need to map these coarse resolutions and create a higher resolution map. So we have to do this AI power downscaling. Sorry for the white on almost white there. That makes the data only available to the stakeholders, for the forecasters that actually create the stuff that we're interested from a public government sector, or for the industry. And of course, for everyone like you guys in here, probably most researchers and scientists, it's much more fun working with high resolution data than with really coarse resolution, where you just have like a bias of 1 point for all Switzerland. Now, I'd like to. Now, some of the show has been stolen by Noel before with the flood use case. I don't have so many kind of nice pictures, but I just wanted to show you about like how we do it from a conceptual, from a data flow and model flow perspective. So what we do, we start by mapping the current situation by semantic segmentation. Typically, we're using increasingly also foundation models in the geospatial image domain. I'm not sure. I mean, I think one of my colleagues has presented something this morning. I think it was in another session. This serves us then as a reference, also to benchmark the tools that we have and to validate them. Then what we need, if we want to predict the future, we have to kind of get an idea of what kind of weather do we have in the future. But we don't want to predict like the weather in 50 years. I mean, that's not going to be meaningful. We have to understand what are the extreme weather events that actually can cause damage. For that, we have kind of a weather generator. It's based on an extreme value theory. It can also estimate return periods of extreme weather. So we can have like a 1 in 100, 1 in 1,000 scenario. And that gives us then kind of realistic precipitation patterns that we can ingest into a physics-informed model. It's like what we've heard before, also flood models with soil properties, all what we need to actually be able to predict it. Then we go take fundamentally the weather generator or the actual weather scenario from past events, use that to validate our simulation tool, and then we can start predicting. Once we have the extent of the flood, the important thing and relevant for the stakeholders is not how much flood we're going to have, it's how much is that going to destroy my asset, how much is it going to impact me. So for that, we use the so-called impact functions. They're kind of relatively simple functions, but really hard to calibrate. Once you have them, once you have for example, the flood height, it gives you an indication with your vulnerability of your asset how much damage is actually that event going to cost in the future. Now, everything of what you just heard relies heavily on data, on geospatial data, and the good news here is there's a lot going to be coming, even more. It has changed dramatically. You see the number of satellites that have been launched recently. Not everything is Earth observation. There's a lot of communication satellites from Elon, but also a lot of Earth observation, and also the data in terms of recurrency. So the revisit time of satellites, the resolution that we can get today compared to even 10, 15 years ago, this is dramatic. I mean, today we have daily or sub-daily revisits with resolutions below 1 meter, while like for a long time we had like Sentinel-1 and 2, which was like roughly at 10 meters. So I think that really helps us in our quest. But now we have all this data and the greatest and latest AI tools. Do you think a lot of people actually in the Swiss economy are really using those? Like, I'm just talking SMEs, startups, for their daily business, not as a research project. And to be honest, if you look at where AI for climate mitigation adaptation often goes, it's often the big companies that want to have like an assessment tool that is a one-off, and then it's not going to be made public or accessible to others. We have a lot of research which is uses proprietary interfaces. I mean, it's getting better. I have to admit, everything is getting better, but it takes time. A lot of it is poorly documented. Reusability is limited. Scalability may be or may not be possible. Then it's poorly maintained. Project is being closed. A lot of it ends up in a drawer. So it's a lot of resources from a society that we kind of lose there. And often the use of these tools is still, I mean, meant for researchers or other highly skilled people. So the question is, what shall we do? And kind of this question to what can we do to make AI more accessible to the ones that actually need it down at the bottom to make society and economy better in the long term and to help us prevail in the face of climate change. That was a question we asked ourselves, and we also asked that to well, that was too fast. To all these people as well. This is like a lot of climatologists from tons of, it's about 50 people from about 30 different organizations, all in Switzerland, trying to understand, hey, how can we make it more accessible to the ones that actually need it? And in the context of that, we kind of started writing a white paper to try to address that. So we said, okay, what's the main, oh, I'm over time, sorry for that. What's the main chapters? You see that here. So impact, kind of what I already talked about, the technology disruption of AI and data. And then we have, in the end, we come up with some recommendations. It's about 2 pages. I'm just showing you like 2 paragraphs. So it's about, we really would like open science principles to be implemented throughout the society. And for that, we're not pointing at the researchers, but we're pointing at the ones that give the money. And they have to make sure that to implement these initiatives, they need to be incentivized by, if you don't do it, you're not going to get the money. It's not like if you don't do it, we're going to say, whoa, not good, but here's the money anyway. So it needs to have consequences if you don't implement these kind of technologies and concepts. And on the researcher side, of course, you should be aiming at kind of creating reusable code, your entire code base, and for that you have to do versioning, testing, validation, and you should be using tools for the deployment that everyone else is using as well. And ideally, you're going to do that because you're incentivized, because you're not going to get money with your research project, because the government is not going to fund you. With that, I would like to close, and thank you for your attention. Looking forward to some interesting questions later on. And again, my head here is not so much as an IBM researcher, but more like as an editor and co-author of this paper from SATW, which will come out in one or 2 months. So check it out. It's only 120 pages.